In this video, we're going to talk more about nuclear decay equations and work on being able to predict an isotope that'll form if we know parent nuclide and the emitted particle or the type of decay that it undergoes. And so when we're doing these types of problems in general or thinking about them, we're always going to use the same structure for our nuclear decay equations with that parent nuclide on the reactant side. Yeah, and the resulting product or daughter nuclide on the product side. And then the particle that's emitted. We're typically going to be solving for the new isotope. Sometimes you'll know what an isotope decays to, and you're trying to find out what kind of radiation is emitted. So there's a couple different ways to approach these problems. But in general, we're going to say that the atomic and the mass numbers are conserved between the parent and the daughter nuclides, which means that the daughter nuclide and the emitted particle, if you take the sum of their mass numbers, they'll equal the mass number of the parent. And if you take the sum of the atomic numbers or the charges, it'll equal the atomic number of the parent nuclide. And you can see that here in this example with thorium-232. I think it's thorium. I'm sorry if I'm misremembering my chemical symbols. If we know it undergoes alpha decay, we know two pieces of this equation already. We know what we start with, and we know one of our products. So to figure out what our daughter nuclide is, we know that we have to have this 90 equal whatever the atomic number of that isotope is plus 2. And so we can solve these really simple algebraic expressions, oftentimes just by inspecting it, and find out, oh, well, if I've got something that has an atomic number of 88 and if there were two more things that came from that alpha particle, I would have that thorium-90 and so we'll do the same thing with our charges as well, or our mass number. The mass number plus 4 has to equal this 232, and that means that that mass number has to be 228. We just subtract 4 from our 232. And so now this 88, this tells us the element that we produce. And so I'll find that on the periodic table. And this is the mass number that'll tell me the isotope that it is. So I can get more information about the number of neutrons that are actually in this isotope that forms. And so if we do go to our periodic table, hold on. So if I look at my periodic table, which I had to go get, I'll see that 88, if I look it up on the periodic table, is radium. So that means this daughter nuclide is going to be radium. I can put that 88 here, and my isotope number is, or my mass number is 228. And so the expectation is that you can do this kind of prediction for any of the different types of radioactive particles that we have, or emitted particles that we have: alpha, beta, positron, and gamma. And I think one great way to do this is to show one example, one isotope that decays all three ways, just so you can see the difference in product daughter nuclides that will form. So let's do that here. Let's use gold 197. And now gold 197 doesn't undergo all three of these different types of decay. Gold does, but different isotopes of gold undergo different types of radioactive decay. So this is really just a thought experiment to see the differences between the two. So we'll walk through all of these: alpha, beta, positron, and gamma. And we're going to be using this general structure right here for solving these. So let's start with an alpha particle. So we'll have, and I'm just going to do this right next to each of these. So we'll have 197 as our mass number, 79 our atomic number for gold. And that will decay to an alpha particle. And you can use that helium symbol or the alpha symbol, whichever you prefer. And now my daughter nuclide will be 2 plus, let's call it Z, will equal 79. So I'm solving for Z. Um, and that's going to make Z equal 77. And then for my mass number, I'll have 197 has to equal Y plus 4. So it'll be 193. And so I'll go to my periodic table and say, okay, well, what's 77? It's iridium. So my answer will be, or my complete one would have this iridium right here, the alpha particle, and the gold. And just like a chemical equation, we'll make sure there's a plus symbol in between them as well. All right, so let's try that for a beta particle now. So same starting point, my gold 197. And now I'm going to have something with a mass number of 1 or 0 and -1. And again, you can do the beta or the E symbol. So 79 is going to equal -1 plus 80. And my 197 plus 0 will equal 197. And so my product here is going to be mercury. For my positron decay, again, we start with the same thing. And you should, unless we're doing electron capture, you should just have one thing on the reactant side, your parent isotope. This time it's a +1 charge on this particle. And so that means 1 plus 78 will actually equal my 79. So I'll have an atomic number of 78, and I still have that mass number of 179, and that's going to be platinum. Now, gamma radiation sometimes accompanies these, and so you might see a particle that undergoes beta and gamma, and so then you would just add gamma, right, at the end, because it's just going to be energy. But you might also see it like with technetium and a few other things where the isotope becomes more stable as it releases energy, and it only releases energy and it doesn't release a particle. If that was the case for this one, we would write it like 197, 79 for my gold. And then we usually have some way of indicating the difference between the two, between a stable and non-stable. And sometimes I've seen it as a little m. And then it'll go to the same thing because it's not actually changing the mass at all. Sorry, gold still plus gamma radiation. So let's look at one more type. Let's look at electron capture. So this is a case where an electron from one of the inner orbitals is pulled into the nucleus. And it's going to combine with a proton to form a neutron. And so we'll see if I had a proton and I pulled in an electron, this would cancel my atomic mass or charge. And so I would have a charge or atomic mass of 0. And then my mass numbers are going to add up to 1. And that's how we would describe a neutron. So in this case, that electron particle is on the reactant side. And again, I'm still going to use this idea that my reactants and products have to sum to the same value for my mass number and my atomic number. And so my 79 minus 1 will give me a 78. And so electron capture will produce a platinum 197, which was the same result we had for positron emission. So we get the same product, whether it's electron capture or positron emission. All right. Here is a summary table out of a textbook I like that shows an example of each one of these different types of nuclear decay for you to reference. And it shows the change in the atomic number and the change in the mass number that you see for each of these types of decay, including electron capture. And what I do like is that it shows the similarities between positron emission and electron capture as well. So this is just in here for reference as you work through practice problems and homework problems. All right, and now we've kind of looked at the overall picture of like how we write out these nuclear decay equations. It's also important to be able to understand what's happening on that nuclear subatomic particle level with each one of these. So let's talk about this in the context of the problems that we just walked through. So for beta emission, when we're emitting a beta particle, that was when we converted our gold 197. Here we go. Into mercury. So what's happening here is we're not seeing a change in the mass number, and so we're really converting a neutron into a proton, and it's essentially taking that neutron and adding a positive charge to it, which is a weird idea. Um, and except that if we think about each of these subatomic particles as having mass and charge, and we usually think of those as describing one thing. We found, and actually a couple years ago, there was a successful experiment where a group was able to separate a proton's mass and charge into two separate beams and then bring them back together. And so this idea that the charge of something and the mass of something are somehow intertwined in this idea of what mass is actually very separable. And that's essentially what's happening in these nuclear like transformations, is that a neutron is able to essentially create itself into a proton and an electron, and the mass doesn't change. And what does change is that this zero right here, I mean, that can become a 1 minus 1, right? And so I can have a positive charge and a negative charge. And so that neutral charge essentially splits, and something with no mass but a negative charge goes flying out of the nucleus, and that neutron has transformed itself into a proton. And I personally think this is kind of one of those fun things in chemistry that you get to think about. And you're like, wow, that's actually a really weird thing that nature does. So then looking at positron emission, this is when we saw our gold become platinum. I'll put it up here real quick. So this was, so in this case, what we're seeing is a proton is going to separate its mass and its charge, and it'll be a neutron. That is its mass, and its charge is going to be ejected from the nucleus. And so it's taking that positive charge and it's removing it from the nucleus as a positron particle. So it has mass, it's just very, very, very small. And then you're left with a neutral particle, the neutron. Now, like electron capture is kind of the opposite, right? We have a proton that you combine with an electron and you form a neutron, which is basically the opposite of beta emission. It's just, you're just literally flipping that entire equation, where you capture an electron, you pull it in, and that negative charge and the positive charge of a proton combine to form a neutral charge, the neutron. Give these problems a try, and I'll go over them in the next video. And it's just practicing writing up nuclear decay equations and making sure that you get the formatting of the equations correct.